Okay, good afternoon, ladies and gentlemen. How are you guys doing? Alright, so I'm reading the chat on the side. Hopefully you guys are all doing well. And today, because I actually have a Calculus 2 exam 3 tomorrow, so I decided to just do one of the old exams that I have. And if you are in my Calc 2 class, welcome, and then good luck on the test tomorrow. By the way though, I didn't print out the file, but you guys know it. The file is in the description. We have a total of 13 questions. The first 6 questions are multiple choice, and then the rest of the questions will be in the short work format. All right, so that's usually my mix for my exams. Okay, so hopefully you guys are doing okay. No, this is not pre-recorded. This is live stream. And here we go. First question. Well, we're going to calculate the series as n goes from 1 to infinity of 1 over n squared plus 3n plus 2. And we are supposed to get value out of this. And as you can see, the bottom right here can be factored. And we'll just go ahead and do that. N plus 1 times n plus 2. And yes, this is going to be a telescoping series. And let's just go ahead and do this real quick. So this is the series as n goes from 1 to infinity. Well, we are going to have some number over n plus 1 and then add it with some other number over n plus 2. Here's the deal. Go ahead and cover this up and let n equal to -1, right? And then you put it in here. 1 over -1 plus 2 is 1 over 1, which is just a 1. All right, and then look at this. To figure this out, we go back to the original, cover this up, and then plugging n equals -2 into here. And then we get 1 over -2 plus 1, which is just -1 on the bottom. All in all, it's just -1. All right, so usual telescoping series. Now, check this out. This is the fast way. They are of the same kind, but they are off by 1 term. Therefore, the way we can do it is go ahead and plug in 1 into here, and that will be the first term. So we just write down 1 over 1 plus 1, which is 2, of course. And that's it. That's the leading term pretty much. And then we are going to just write this down. Right? Remember 1 term in the front and then 1 term at the end. So this right here is minus, and then we have the 1 over n plus 2. Right? So this is pretty much the deal. And don't forget, we are going to take the limit as n goes to infinity. So this is actually the nth partial sum of this telescoping series. And then the truth is, when we have n goes to infinity, this guy nicely goes to 0. Therefore, the answer is just 1 over 2. Right? So, usually the first question, like a little warm-up, little appetizer, not so bad, right? And definitely need to know the answer for that. So, that's it. All right. Hello, Abdul Jabbar. Nice to see you again. And then Asha and everybody else. Nice. Oh, Noah, it seems like you finished the test already. Oh, David, Gus, hello. I still have to work on your differential equation, but I've been busy with my class lady, so yeah. Okay. I think this is more fun than... I think solving exams is more fun than usual lecture, right? Because I did a lecture for the series, and I don't know. We'll see. Anyway, let's see if I can fit in number 2 here, but like... no, I'm going to just do number 2 for you guys that on the whole board. All right, this is number 2. I give you guys a series as n goes from 1 to infinity, and then we have 1 minus 1 over n, and then raised to the nth power, and we have choices, right? So the first option says we are going to see that this right here converges by the root test. Root test, right? Or part B says this right here diverges by the root test. And then C says this right here converges to 1 over E by, well, in my class, I call this the fact. So I'll just write that down, which is Well, you should know that. And then D, this right here diverges by test for divergence. And then you know, choice E, wow, this is the best option ever. I don't know. I don't care. This is option E. All right, so go ahead and leave the answer in the chat right now. We'll be looking at the chat. So go ahead and let me know what do you think, what the answer. Come on, let's do it quick. So which one? All right, if you select choice E, this is automatically false. All right, just playing. Okay. This is just live stream. That's why I put this option just for fun. And then in fact, I put it on the file just for fun. And now let's be more serious. Okay, so here's the deal. If you look at this, 1 minus 1 over n raised to the nth power, well, this reminds you of the fact a lot, right? But if you just kind of look at it, let me just tell you guys this on the side. The fact says, if you take the limit as n goes to infinity of 1 plus a over n raised to the an power, raised to the bn power, well, this gives you e to the ab power, all right? So of course we can use that. But you see, this right here is actually our an. This is the series of an. Well, if you take the limit of an, let me just perhaps put this down in blue. If you put the limit as n goes to infinity of an, which is going to be the limit as n goes to infinity of this thing, right? 1 minus 1 over n raised to the nth power. By the fact, well, a is equal to -1 right here, and then b is equal to 1. So let's just put that down. Therefore, the answer is e to the -1 times 1, which is just -1. But you see, the moment that we're doing the limit as n goes to infinity of an, this is to test for divergence. This right here, well, don't just write it down. Do not choose option C, because we're not asking for the an. We're asking for the series of an. So C is not correct. C is not correct. Right? C is not correct. Once you notice the limit of an goes to e to the -1, and you see this is not equal to 0, in fact, we can say that this diverges by test for divergence. So you just have to remember the difference between an and the series of an. Again, this question is about the series of an, and if you take the limit of an, if it's not equal to 0, congratulations, we can say that this right here diverges. And now you might be wondering, how about A and B? Well, they are the opposite options of each other, right? So shouldn't that be one of them must be correct? Well, that's not true, because sometimes when you are doing the root test, you may not be able to draw conclusions. Just real quick for you guys, if you want to use the root test, right, this right here, we will have to check the limit as n goes to infinity, and then we do the root, right? The nth root, and then put the absolute value. And then you put this in here, which is 1 minus 1 over n raised to the nth power. Well, this and that cancel out, and you just have to do the limit as n goes to infinity of 1 minus 1 over n. When you have infinity to here, this thing goes to 0. Thus, you see this right here is actually equal to 1. If you do this limit, the nth root of the an, if this right here gives you 1, unfortunately, root test is inconclusive. So this is the sad face situation. We cannot draw any conclusion with the root test. So that's why A and B are not correct. Even though this is a divergent series, but you cannot say it diverges by the root test, right? So hopefully that makes that clear. And of course, for the people who choose option E earlier, yeah, we all have the sense of humor, of course. All right, so this is question number 2. All right, so after today, yeah, that will be done for the series. And then yeah, my students have a test on this tomorrow, and this is just like a little warm up for them. Or yeah. Okay, let's look at the next one. All right. Given, right? Given the following, right? And then the question is asking, which of the following cannot be plugged in? All right, so I just want to write down the question real quick. Cannot be plugged into the following, which we have x minus 1 over 2x squared plus 1 over 3x to the third power, and then minus dot dot dot, and then we say this is equal to ln of 1 plus x. And I'm going to give you guys options. Option A is 2, and then B is 1, C is 0, D is 1/2, and then E is negative 1/2. Okay, so if you guys take a look right here, which of these x values, these right here are the x values, right? So yeah, which of these numbers cannot be plugged in into the x right here? What do you guys think? And again, these are the x values. Right? This is like x is equal to 2, x is equal to 1, x is equal to 0, and so on. All right. The majority of you guys are saying A, which is correct. Well, keep in mind, this right here is the power series for ln of 1 plus x. For this right here, you have to remember that the interval of convergence is going from what? -1 to 1. And you have to remember that you do not include the -1, but you do include +1. So this right here is the key, right? This right here is the key, because it looks totally okay to put 2 into this right here. Of course, we can just do ln of 1 plus 2. This is totally okay, right? But the problem is that you cannot put 2 in there and say 2 minus 1/2 and then 2 squared and then all that stuff and it's equal to this. This is not okay. Why? Because 2 is not inside of this interval. Therefore, the answer is A. 2 cannot be plugged into this power series. So this is the concept of the power series and also the interval of convergence, right? And then you see 1. It's actually okay because that's just like all the way at the end. -1 wouldn't be good though, but I didn't have -1. These numbers, they are all inside of this interval, so they are all good, right? So this is number 3. So for my exams, especially multiple choice questions, I usually test the concepts, yeah, for the students to see if they understand the technical details or not just computations. 0 is okay. Yeah, earlier when we plug in 0, it's totally okay. All right, number 4. We want to find the first 4 non-zero terms. So first 4, and then the key right here is non-zero, right? First 4 non-zero terms for the power series for did I put down f of x? I didn't, so I'll just say for sin x at a equal to pi over 4, right? So this right here, we just have to do the work for this. Not so bad. All right, power series for sin x at pi over 4. Perhaps the safe way to do this is just do the table. So let's go ahead and do the table. We are going to have some n values, and then this is the nth derivative. And then lastly, we are going to enter the Taylor formula, namely the nth derivative of the function. And we are going to plug in the a, which is pi over 4. So let me just put that down. And then divided by n factorial. So the last part right here is just the Taylor formula. Well, let's see. 1, 2, 3, 4. Hopefully this is enough. Right? 0, 1, 2, 3. Starting with just sin x, because the zeroth derivative means the original function. And then just differentiate this a couple times. So we get cosine, and then negative sine, and then negative cosine. All right? Okay, so when we plug in pi over 4 into sine, remember your trick, of course. Once we put this in here, we get 1 over square root of 2. And perhaps I will write it down like this, so I have enough space. 1 over square root of 2. And then over 0 factorial. Right? And in fact, when you plug in pi over 4 into cosine, you also get 1 over square root of 2. So this is pretty nice. Over that. And then you have the 1 factorial. And then you keep going. This plugged into there, you get negative because of that. 1 over square root of 2 over 2 factorial. And then lastly, negative 1 over square root of 2 over 3 factorial. Yeah. So I'm going to write down the answer for you guys. Ladies and gentlemen, sine x, when a is at pi over 4, the first term is just going to be this. And we are not going to write it in the sigma notation because I put this down in the multiple choice format. We just want to write down expanded form. So the first term is this. And that looks like just 1 over square root of 2. And perhaps I'll put this down in red. Yeah, to make it stand out a little bit. 1 over square root of 2. And again, this is at a equal to that. Next, we're going to add this, and 1 factorial is just 1. So we have 1 over square root of 2, and then we multiply this by x minus pi over 4. Remember, a is at pi over 4, so you have to do x minus pi over 4. So that's the second term, and the next we are going to have the minus. So I'll put this down right here, minus. And then we have 1 over 2 factorial, which is just 2, and then we have the square root of 2 right here. And we have x minus pi over 4, and then raised to the second power. And lastly, we have that, which is negative 1 over, again, square root of 2. But we have 3 factorial, which is 6. And then you have the x minus pi over 4 raised to the third power, and so on, so on, so on. Da, da, da. Yeah, so this right here is the answer for it. All right, Adam, thank you, the microphone. And since you guys are here, this is how I do it. You guys notice that this is just a regular mic on the phone, and then this is the Pokeball. Yeah. I was going to do a video on how to create your Pokeball mic, but since you are here and you're asking, since you say you like it, let me just show you that. That's the secret. Right? So this is just a typical computation question. And now let's move on to number 5. So for number 5, we have another computation question. We are going to do the series as n goes from 2. This right here is meant to be a 2 to infinity. And then here we have negative 1 raised to the n plus 1 power. And then we have 1 over 3 to the n. And we're trying to figure out what's the value of this series. Does it converge? Yes, it does. How? You can use the alternating series test because we have this factor, and then just go ahead and write down the Bn goes to 0 and Bn decreasing and things like that. But better yet, this is not just an alternating series. This is a geometric series. This is how. Check this out. This right here is equal to the series as n goes from 2 to infinity. Have a look right here. This is the same as saying negative 1 raised to the first power and then times negative 1 raised to the nth power. Yeah. Break it down and then multiply by 1 over 3 to the n. Pair this up together and we can write this down as the series as n goes from 2 to infinity. Pay attention that we do have this negative 1, so this is negative. But this and that together, we can write it down as parentheses with negative 1 over 3 inside, and then raised to the, just kidding, raised to the nth power. Have a look. This right here is a converging geometric series. And it's a multiple choice question. You don't really have to show that. But be really careful though. n starts with 2. The first term is when you put a 2 in here, so you get negative, and then negative 1 over 3, and then raised to a second power. This is the first term. And then over 1 minus the common ratio, which is this. This is our r, and just put that down, negative 1 over 3. Right? So that's that. And just do the math real quick. This is going to be negative 1 over 9 on the top, over, this is going to be 4 over 3 on the bottom. And let's multiply the bottom and the top by 9. Simple and nice, yeah? Oh, look at this. This and that cancel. We have negative, and this is a famous number. Yeah, I made this on purpose, but even now. 12 on the bottom. Ladies and gentlemen, this is negative 1 over 12. Look at that. How cool is this? All right, so that's number 5. Why are 4 of 5 answers A? This is just, I made up this right here. I put together this right here just for the live stream. And because I'm going over this right here, so I don't really, I didn't really care about like the options in terms of like where the options are. Maybe I should just do, I shouldn't tell you guys this because just in case my students are actually in the live stream right now. Maybe I should just make all the answers tomorrow like OBs or maybe OAs. Yeah. Maybe OAs, I don't know. Yeah. Okay, this is the Pikachu question. If you guys look at the file already, but I will tell you guys what this is about. Here you are given a power series. This is a series as n goes from 1 to infinity, and then we have, this is negative 1 to the n over n squared, 3 to the n, and then x minus 2 to the n. So we are given the power series. Why is this a power series that you ask? You see the x right here. So this is actually a series representing a function, but we just don't know what the function is. But we do know the following. So it's pretty much like given r is equal to 3 and a is clearly equal to 2, and we want the interval of convergence, right? In fact, again, it's multiple choice question, so it's already a quicker question. That's why I give the radius of convergence equal to 3. If this is not given, then you can test this out. R is just equal to the limit as n goes to infinity of the absolute value. Look at this as Cn, right? This is a Cn. And just go ahead and do Cn over Cn plus 1. And you will end up with 3. But it was given, so that saved you some time. Anyway, based on this, we are trying to see the interval of convergence. So we will have to be really careful. And again, you will have to understand what does this mean. Have a look right here. We have x minus 2, right? The center is at 2. The idea is that here is the center at 2. Because the radius of convergence is 3. Because the radius of convergence is 3, that means you can go from 2 to the left 3 times and you end up with negative 1. And then you can go from the center to the right 3 times, so you end up with 5. With that being said, this will give you the interval. But the problem is that we do not know what will happen at the endpoints. Now, let me ask you guys this. Well, yes, we can take all the numbers inside, right? But let me ask you guys this. Have you guys seen the notation like this? Have you guys seen the notation like that? Have you guys seen this notation? No? Seriously? You have not seen this notation? You shouldn't, because I just made that up. The reason is because we do not know what will happen at the endpoint. That's why we don't know. That's why you didn't know what the notation means. But it's okay, because all we have to do is just test it out. Check this out. Remember, these are the x values, right? These are the x values. So we just have to check when x is equal to -1, plug into here and see if that series converges or not. So let's go ahead and do that right here. So we are going to check when x is equal to -1. Because remember, we still have to figure out, do we use bracket or parentheses? All right, so plugging -1 to this right here, we are looking at the series as n goes from 1 to infinity, -1 to the n over n squared 3 to the n, and we have -1 minus 2 to the n, like so. Well, this is -3, right? So let me just write this down. This right here is, let me just put that down. This is the series as n goes from 1 to infinity. We have -1 to the n over n squared 3 to the n, and then this is -3 to the n. Well, -3 to the n is the same as -1 to the n times 3 to the n, right? So just work that out and you get this. This and that cancel nicely, and -1 to the n times -1 to the n becomes just +1 all the time. So this right here is actually just a series as n goes from 1 to infinity, and then we have 1 over n squared, which clearly converges by the p series. Yep. So in fact, I will come back here, and then I'm going to, erase that, and then use the bracket. Okay? So now we know about -1. Well, for 5, do the same thing. So I'll put it down right here. We are going to check when x is equal to 5. Put the 5 in there. So we are looking at the series as n goes from 1 to infinity. Yeah, I know how you guys feel. Let me tell you, one reason that people don't like about series is because we have a lot of things to write down. That's why. But anyway, this is what we have. This right here is the same as 3 to the n. So altogether, this is a series. N goes from 1 to infinity. We have -1 to the n over n squared 3 to the n, and then this is 3 to the n. But this and that cancel nicely. This is the alternating version of the 1 over n squared, right? The alternating version of this. It also converges. You can do the alternating series test just to be proper, but it's a multiple choice. Once you see this, it converges, then that's it. So we can come here and then erase this, and then we'll say, hey. In fact, we include both endpoints. Therefore, for this question, the interval of convergence goes from -1 to +5. Right? So that's it. Yeah. All right, so continue. And for the people who just joined the live stream, because it looks like we have more people now, there will be a replay so that you can see what we did for the multiple choice part. And now we're going to the shorter questions, right? All right, so number 7, we're going to determine if the following series converge or diverge, right? So number 7, sorry. Number 7, here we have 1 over 3 minus 1 over 6, and then plus 1 over 11, and minus 1 over 18, and then plus 1 over 27, and so on, so on, so on. All right, real quick, go ahead and try to figure out the formula for this. So, what's the formula for these numbers? In the meantime, cheers. No, formula, because I'm trying to write down all the work, so it's not just a matter of converge or not. Well, I helped you a little bit. Yeah? Sigma. N goes from 1 to infinity. Yeah. Okay, a lot of you guys are getting this. Notice that the first term is positive though, and then if we use n is equal to 1, then we will get negative 1 to the n, either plus 1 or minus 1, up to you. Doesn't really matter. Let's put on minus 1, yeah, because you will keep it alternating anyway. And then you will always have a 1 on the top. Check this out. This right here is the same as 1 squared plus 2. This right here is the same as 2 squared plus 2. Likewise, this right here is the same as 3 squared plus 2. And 16 plus 2, which is 4 squared plus 2. And you guys can see the pattern. So all in all, it's just n squared plus 2, like that. So in this case, this is clearly an alternating series. Therefore, we can just consider this to be the Bn. And then just to be proper, let's go ahead and write down the arguments. So first, we are going to check. Remember, there are two things for us to check. We have to take the limit as n goes to infinity of Bn. Does this give us 0, right? Well, this is just the limit as n goes to infinity. Bn is that, which is 1 over n squared plus 2. Yes, we end up with 0. This is pretty clear. Here we go. Number 2. Well, Bn plus 1, is this decreasing? Then I don't know yet, put down a question mark, and then that. Just do the math real quick. I will just write this down. We get 1 over n plus 1, and then we square that, and then we add 2 to it. Is this less than or equal to 1 over the original right here, right? 1 over that. And it's clearly true because the bottom here is bigger, but again, that may just be a little bit more, yeah, short work, yeah. So let's just cross multiply because everybody here is positive, so this goes there, which is n squared plus 2. And is this less than or equal to that? N plus 1 squared plus 2. Yeah, it's totally true, right? Because you can get rid of the 2, and this is bigger than that, so I should say for n is greater than or equal to 1, but yeah. Sometimes when you're doing an inequality proof, the problem is that when you are supposed to stop, but this right here should be really clear that it's true, so you can stop. Therefore, we can draw the conclusion. And the conclusion is that this guy, the series as n goes from 1 to infinity, negative 1 to the n minus 1, 1 over n squared plus 2. This guy converges by the alternating series test, right? So that's it. However, if this question is asking you for the absolute convergence, then in that case, you just take the absolute value for it, and it actually still converges. In fact, this right here converges absolutely. But yeah, let me just do this version. Yeah, let me just put this down for you guys, right? Because I realized I was supposed to check absolute convergence, but yeah, maybe at the end. Yeah, so that's it for that. And okay. All right, number 8. Well, here are the fun ones. We are going to integrate the following as a power series, right? So, part A, integral x e to the x to the third power dx. Wow. I don't think this is doable with the usual method. Use substitution? No. Integration by parts? No. Nothing. But power series? Yes. And this is how we can do it. So perhaps I'll write it down on the side. Just as a reminder, for e to the x, right? Let's just put that down first. When we have e to the x, this right here is equal to the series as n goes from 0 to infinity, 1 over n factorial, x to the n's power, right? So that's what we have. Now we have to get this. So we are going to do x times e to the x to the third power. Well, first, just focus on this part. What do? Just plugging this into there, right? Just plugging x to the third power into here as well. Therefore, we get the series as n goes from 0 to infinity, 1 over n factorial. And we have x to the third power and then raised to the nth power. Okay? And remember, the radius of convergence for e to the x is just infinity. That's nice because if you have the cube root inside, if you put a cube inside of the inequality and then do a cube root and things like that, whatever you do, you'll still get r is equal to infinity. But wait, we're not done yet. There's one more thing right here, the x. If you multiply this by x, all you have to do is multiply this by x as well. So in fact, this right here becomes the series as n goes from 0 to infinity, and we have 1 over n factorial. And this right here is x to the 3n power, but we will have to multiply this with that. So you just add a 1 to it, right? Therefore, this right here is actually equal to that, and it has the radius of convergence being infinity. So this is really nice. Now, we just have to write this down. We will just have to integrate this thing, which is that the series as n goes from 0 to infinity, and we have 1 over n factorial times that x to the 3n plus 1, and then just dx this guy, and perhaps let me just kind of separate this. I shall put this a little bit to the left. I mean, a little bit to the right, but too late. Anyway, this is what we have. Now, this is the easiest question ever. Well, to a certain degree. Once we have the power series, we can integrate this so nicely. Add 1 to the power, so the new power is 3n plus 2, and divided by that. So just put it down somewhere, 3n plus 2. So, ladies and gentlemen, the answer to this right here is just the series as n goes from 0 to infinity. Write down the coefficient, 1 over. Usually, write down the 3n plus 2 first, and then the factorial at the end. And then we have x to the 3n plus 2 power. There's one more thing though. One thing that we are missing. Are we done? Yes, plus c. But usually if you put down plus c here, it looks like the plus c is instead of the summation. So, when we are doing this, I will recommend you guys to put down C plus instead. So that way it's more clear. And that's also indicate that R is infinity, because without the radius of convergence, the form is not that useful. So that's it, right? So that's pretty good. Take a look. All right. There's another one that we are going to do. All right, so for part B, here we are going to integrate inverse tangent of x squared, right? So we are going to integrate inverse tangent of x squared dx. All right, we'll do what we did earlier. So let me just put that down right here. When we have inverse tangent of x, right, of x. So this is just the original one. This right here is equal to the series as n goes from 0 to infinity. Remember that inverse tangent is odd, and for the series, it's alternating. So go ahead and just do -1 to the n because it's alternating, and it's odd, so you will see the odd numbers, but you are not going to get the factorials. That's for sign. I'll just put this down, 2n plus 1, and then you have x to the 2n plus 1. And let me make the x red, of course. So that's what we have. And then I will say r is equal to 1. All right? Technically, I should put down an absolute value. I will write this down right here. I will do this technically. Right? Absolute value of x is less than 1. But earlier, absolute value of x is less than infinity because r is infinity. That's why I say if you take the cube root, you still get infinity. So that's the nice case. Anyway, for this, inverse tangent of x squared yes, all we have to do is put the x squared in here. So yeah, it's just a lot of things to write down. N goes from 0 to infinity. And then we have -1 to the n over 2n plus 1 x squared and then 2n plus 1. So if you would like, just finish this real quick. This is 0 to infinity, -1, 2n plus 1, x to the full n plus 2. Notice though, we should have absolute value of x squared being less than 1. But this is the same as saying absolute value of x squared is less than 1. You can put a square on the whole side, and then you can just take the square roots on both sides, because absolute value of x is positive, so yeah. Therefore, r is still equal to 1. Yeah. Anyway, this right here goes there, so we're just going to put that down. And by the way, I'm not doing a live stream for power series like this because I already have a video, power series marathon. I did 26.2 power series for you guys already. So if you need practice with how to get the form for the power series and also the radius of convergence and things like that, you can check that out, right? Okay, so this is that. So we just put down the series as n goes from 0 to infinity, -1 to the n, and then here we have the 2n plus 1, and then that, x to the full n plus 2, and we have the dx. Okay, this is the happiest thing ever. Add 1, the new power is 4n plus 3, divided by that. Good, we're done, right? So let's just go ahead and write down the answer, C plus this time. And then we have the series as n goes from 0 to infinity, -1 to the n over this. Seriously, this right here, it's not hard, it's just a lot to write down. And then, yeah, and then let's write down r is equal to 1. So with all that, we are done. Oops, parentheses, yeah. I missed the -1 to the n. Where? Oh, right here. Thank you. -1 to the n. Thank you. Yeah, thank you, Tommy. All right, so that should work. All right, couple more questions to go. Okay, so let me see what the question is next. We have, oh, okay, number 9. Number 9, it's a slightly harder one. So series as n goes from 1 to infinity. Here we have 1 minus cosine of 1 over n, right? We are going to test out if this right here converges or not, and of course give a reason for this. Blue pen. Let's just go ahead and try. Yeah, let's go ahead and try. So I'm going to try. The first thing is, it's always a good idea to do tests for divergence. So again, we're just trying. So in that case, that means we're going to check. Again, this is just a try, all right? We're going to check the limit as n goes to infinity of just this, which is 1 minus cosine of 1 over n. Okay, this is the limit as n goes to infinity. Well, in fact, let me just do it like this. Have a look. When you put infinity to here, this right here is 1 over infinity, which goes to 0, but it becomes what? 1 minus cosine 0, which is 1 minus 1, which is actually 0. Does this 0 do us any good? Help me out. I don't know. I forgot. Does this 0 do us any good? 哎，李湘老师你好，谢谢又来。 早安了。Right, does this zero do us any good? No, it does not do us any good. Test for divergence, the zero doesn't do us any good, right? So unfortunately, this does not, this is not presentable, so I will have to cross that out. Now, have a look next. Because we see the 1 over n, maybe it's a good idea to do limit comparison test. So let's see. Try the limit comparison test. Well, this 1 over n, the series for that we know much better. So I'm just going to put this down. We know that the series as n goes from 1 to infinity, 1 over n, this thing diverges, right? But if you want to do the limit comparison test, let's go ahead and check. We check the limit as n goes to infinity. We put this down on the top, which is 1 minus cosine of 1 over n, and then over the one that we know much better, which is 1 over n. So this is another kind of limit that we do, right? The limit comparison test. Well. You know what? We get 0 over 0. And you know what? Right here, I'm not going to use L'Hopital's rule yet. Because this is n. This is one of the notations that I really don't want students to do. DDN, please don't. Please don't write DDN because n is meant to be a positive whole number, or maybe 0. DDN, no, just don't write that. No, just don't. But what you can do is you can just check the check and just check. Let me just write it down in red and black. You check the limit as x. You change the n to x, right? 1 minus cosine of 1 over x, and then over 1 minus 1 over x, like that. Please don't write ddn. Write it down as x, and then put down ddx. This is the check of the check. Why? Whatever this gets, we will have the same answer for that. That's the idea. But anyway, let's get to work for this. Differentiating, right, but still write down the limit as x goes to infinity. 1 goes away, the derivative of negative cosine is positive cosine. No, just kidding, positive sine. And then 1 over x, but don't forget the chain rule, multiplied by the derivative inside. Namely, negative 1 over x squared. Over the derivative of 1 over x, which is negative 1 over x squared. You see? This and that cancel out completely. When you take the limit as x goes to infinity, you put it here. You get sine of 0 and you end up with 0. Well, because this right here gives us 0, that means this limit is also equal to 0. Now, does this 0 do us any good in the limit comparison test? Does this 0 do us any good in the limit comparison test? Well, remember, for the limit comparison test, right, especially the version that I present in the class, if you end up with 0, no, it doesn't do us any good. It doesn't do us any good. Keep in mind, if you draw a conclusion right now, you will be saying that this right here also diverges. But that's not true. Because this 0 doesn't do you any good. It doesn't tell you anything, right? But the detail for why 0 doesn't do you any good, it takes some more time to discuss. But for now, just remember that if this limit is 0 or maybe infinity, then we cannot draw any conclusion. So unfortunately, this is also not presentable. And what do we do when you have this kind of things happen on the test? Just have to cross it out, and then try again. That's all, right? So, man, this is so much work already. Are we done? No, because we still haven't figured this out yet. All right, so here's the deal, right? Keep in mind, this actually doesn't do us any good. We will still use limit comparison test, but now with this series. Anybody has any idea? Help us out. You might be able to get a cookie if we can help us out. Or maybe some ice cream. Oh hey, that's correct. You do the series of 1 over n squared, but what makes you to do the series of 1 over n squared though for this? But what's the hint? I don't see the n squared. I don't see square at all. So how can we do that? DCT might be slightly harder because that's the direct comparison test. You might have to use inequality, and you might have to come up with. It might be harder to come up with something that you know much better. So, yeah. All right, here's the hint. Yeah, here's the hint. Recall. So just put this down on the side. Recall that when we have 1 minus cosine of an angle, yeah, think about the times that we did integrations. Recall that when we have sine squared theta, hey, this right here, we know that this is what? 1/2 times 1 minus cosine of 2 theta, isn't it? So let me just write this down better, like so. Right? Sine squared theta is equal to this. Wow. This looks similar to that. Multiply both sides by 2. We get 1 minus cosine 2 theta being equal to 2 sine squared theta. Sine theta, like this. Here, as you can see, we want to have 1 over n. Therefore, we just have to let 2 theta be 1 over n. Therefore, theta is just equal to 1 over 2n. So if you put this in here, you get a very nice identity. 1 minus cosine of 1 over n is nicely equal to 2 sine square of 1 over 2n. Very, very nice. So this will give us a lot of hint. So now, let's go back there and let's write it down. We just have to test out the series as n goes from 1 to infinity of this guy. And that's 2 sine square of 1 over 2n. Like that. Okay? Well, we are still going to do comparison, especially the limit comparison. But this time though, let's go ahead and put down what we know. I'm not going to use 1 over n because the truth is this is sine square, meaning sine times sine. So this is actually being multiplied by twice. So let's go ahead and do this. We know the series as n goes from 1 to infinity. Let's use 1 over n squared. And of course, this right here, by the p series, right? It converges. Now, here's the check. Right? Here's the check. And again, this is for the LCT, right? Just keep that in mind. We're doing the LCT. So we're going to do the limit as n goes to infinity. Put this down on the top. 2 sine square of 1 over 2n over the one that we have over there, which is 1 over n squared. Now, have a look, ladies and gentlemen. This right here is the limit as n goes to infinity. I'm going to write it down like 2, and then sine of 1 over 2n times sine of 1 over 2n, and then divide this by 1 over n, and then 1 over n. Oh, why did we do that? Well, check this out. I'll do a real quick substitution. I'm going to let theta equal to 1 over 2n. And as you can see, as n goes to infinity, theta will go to 0. So perhaps I'll just write it down right here. Let theta equal to 1 over 2n. And we get limit as theta goes to 0, right? Because you put infinity to here, so theta goes to 0. And we have 2 sine of theta times sine of theta, right? And then over, man, if theta is equal to 1 over 2n, that means 1 over n is equal to 2 theta, right? So this thing is 2 theta, and this thing is also 2 theta. All right? Now you know what we can do. First, we can cancel the 2. And then here's the best part. This is the limit. As theta goes to 0, sine theta over theta goes to 1. And this right here also goes to 1. And this is legit because the limit of a product is a product of the limit under the assumption that the limit exists. They do. So altogether, we just have 1 times 1, and we have a 2 on the bottom. So this right here is equal to 1 over 2. Now, does 1 over 2 do us any good? How are we going to use the 1 over 2? Do not just put on 1 over 2. Remember, for the limit comparison test, the limit that you end up with, as long as it's greater than 0, and it's finite, okay? 1 over 2 is of course not infinity, then you get to draw a conclusion. And the idea is that once you have the 1/2 right here, you are saying the ratio of this and that is about 1/2, right? So this and that behave, just about like half. You can just think about like half of the size. So this right here converges, that right here also converges. Therefore, we'll just say conclusion here, conclusion. That guy, originally, the series as n goes from 1 to infinity, 1 minus cosine of 1 over n, also converges by the limit comparison test. So you see, this is actually the answer, not the one that we got earlier. That's why I crossed out the blue one, right? So have a look on that. This is one of the harder one. All right. So just a couple more questions to go, and then, yeah. All right. Here we go. Next one. Oh my God, this is my favorite one, because you will really have to know the material if you are able to give example of certain things. So for number 10, we are going to talk about the examples, right? Give an example. So I'm not asking you for the answer, I'm asking you for the question. All right, part A, we want an example that series as n goes from 1 to infinity of an. We want an example of that, so that ratio test will give inconclusive result. Yeah, let me just put that down here. I was trying to do part B here, but I don't think so. But anyway, have you ever wondered why sometimes the ratio test just doesn't work? And yeah, give me an example for that. An example of a series that you cannot use the ratio test. The example that the ratio test cannot work. Much harder, huh? Oh, hey. Uh, uh, um, I don't know what to say about your answer. I think that's actually legit. If you do the series of 1, that's actually quite legit, I would say. Alright, I'm going to put down like a honorable mention, like a special mention for this. This is by Jorge, as I'll just put this down right here. This is by Jorge. Man, I love to do live streams because like you guys always give me like creative answers. By Jorge, like the example that he gave us is the series of 1. Why? Alright, why? Remember the ratio test is what? Remember, we have to do the limit as n goes to infinity of the absolute value an plus 1 over an. We want it to be equal to 1. That's what will make it inconclusive. So, if you look at this right here, this is an, which is always 1. If you do the limit of n goes to infinity of an plus 1 over an, of course this is going to be 1. Oh my goodness. Man, I thought this was a great question like on the exam, but like yeah, that's totally legit. So yeah. Anybody? Well, I saw some of you guys give me the answer already. But by the way, let's see. You see, we get 1, and this thing right here obviously diverges. Okay, obviously because it's always add 1. But let's see more examples. Let me see. Let me look back to the chat. Let me see the first person who gave the Alan actually. Okay, this is by Alan. And this is actually one of the answers that I have in mind. In fact, any P series will work. So this is by Alan. So I'm just looking back at the chat to see who gave this answer first. So if you do the series of 1 over n squared, well, if you do this real quick, you will see that we have to do the limit as n goes to infinity. Well, an plus 1 is just going to be 1 over n plus 1, and then we square, and then divided by an, which is this. In fact, this right here is the limit as n goes to infinity, and you don't need the absolute value because everything's positive. Put this to the top, and then this is still on the bottom. But this right here can open it, which you get n squared plus 2n plus 1. And you see this, that should give you the limit of 1. Again, inconclusive. Yeah, so the ratio test does not work for this either. Any P series will work, yeah, for this question. And in this case though, you see, this right here actually converges. And let me just be more legit, by the P series. This right here clearly diverges because the limit of, let's just put down by test for divergence. Yeah, because it's always 1. You never get to 0 for the an. So that's that. So I was just looking for any kind of P series. That will be it. Yeah. Yeah, Dr. Shake. Yeah, I totally agree. I was so shocked about like when he gave that answer. That was really cool though. All right, maybe I have to think about like better questions in the future now because clearly I never thought about that, and it's logically correct based on what the question is asking, you know. Okay. One of the things I like besides solving questions is, you know, of course, come up with questions. And yeah. All right, this is the classic one, right? Part B. Give a series, right? Give an example of an, and an is not equal to 0, but the series as n goes from 0 to infinity of an does equal to 0. In fact, I went over this in my class yesterday, and I just want to see if my students remember it or not. So yeah, but if you have not seen these questions before, think about it. Yeah, Think about it. Hello, Simon, how are you? Right now, we are trying to figure this out. We're trying to figure out an, and an is not equal to 0 for on. But the series of an is in fact equal to 0. I'm pretty sure if I didn't put this down, people would just say the series of 0. Yeah, about that, so watch out. Alan. Okay, I will take that for the answer, but you will have to write a formula for that. If you guys saw what Alan did earlier, oh my goodness, this is by Alan, all right? He pretty much just took an to be, well, it's not equal sign, I'll just put on like a arrow, 1, and then -1, and then 0, 0, 0. But I did say an, well, yeah, I guess this might work because I only say an is not equal to 0 on the file I say for on, right? Because you have a lot of you have a lot of zeros, but like it's not everybody is equal to 0. I want a formula this time. I want a formula. So no, not this one. All right, so I don't know how you guys feel about it. Just seriously, maybe not, yeah. Because I want a formula slightly more interesting like that. I just had to think about how to phrase this so that you can actually give a formula. If you can give a formula for this, explicit formula though, non-recursive, okay? I think that would be legit, yeah. Well, Michael, yeah, again, that's what I was. I want a formula. I want a formula. It's not just a write out. Yeah. Yeah. Because otherwise, there's like a classic series that you can do for pi, you know. Yeah, just give a formula. Let's see. Well, no, the answers that you guys give are not correct. Okay, Alan, I want the explicit formula, not piecewise. So you have to make sure that your formula works when you plug in 3, you get 0. When you plug in 4, you get 0. When you plug in 5, you get 0. Yeah, explicit formula, not piecewise. Yeah, I know, I'm just kind of being, how should I say it? I don't know. just give a formula. It's more interesting that way, okay? Alright, so Ash, right? So we have a good idea here. This right here somehow just go ahead and use sine or cosine. And we are talking about series, so we are going to do the power series for this. Wow, it's 2:40 already, but let's go ahead and finish this real quick. Anyway, let's use sine. Here's the deal. Sine x, right? Sine x is equal to the series as n goes from 0 to infinity. And remember sine's odd and it's alternating, so go ahead and put down -1 to the nth power. And this right here, you have the factorial. So 2n plus 1, factorial that, x to the 2n plus 1, right? So that's pretty much what we have. Plus 1. And the best thing about this is that you can use for all x. Yeah, spelled it wrong. This right here is true for any x values. And this is just like another way to say the interval of convergence is going from -infinity to +infinity. And you just have to think about sine of what will be 0? Sine of pi will be 0. So I just have to put down let x equal to pi, and then we will get sine of pi. But perhaps I will just write this down here first. You will see that the series as n goes from 0 to infinity, negative 1 to the n over 2n plus 1 factorial, and then you have the pi raised to the 2n plus 1. And just for fun, I'm going to expand this for you guys. First, if you put 0 into the n's, you get pi. Next, you are going to get minus 1 over 3 factorial, and then pi raised to the third power. And then, next, you are going to add 1 over 5 factorial, and then pi to the fifth power, and then so on, so on, so on. This right here is just equal to sine of pi, namely, you will end up with 0. And I think this is so cool. Look at that. Pi minus 1 over 6, pi to the third power, plus 1 over 120, pi to the fifth power, and so on, so on, so on. You actually end up with 0. And none of the terms is 0. So I'm not using 0 at all, but we end up with 0. Very nice, huh? All right, cool. So I love to give like example questions because this is the way that you can really force the students to think, right? So, yeah. All right, so 10 questions, and then let's watch all the time because I have another class. All right, number 11. So here's the question for number 11. We are going to say let the sequence an be n factorial over n to the n. Part A, the question says specifically, does an converge? Does an converge? What do you guys think? And perhaps I'll also write down part B here. Does the series of an converge? Okay, so let me know what you guys think. Part A, converge or diverge? Hello, math nerd. Good to see you. Yeah, maybe you put in the chat earlier, but I didn't notice. Yeah. Hello, Kiro. And let's see, does an converge or not? And if so, can you guys tell me what does it converge to? Yes, this right here converges, and this is how you do it. Remember, if the question is asking does the sequence converge or not, just go ahead and check the limit as n goes to infinity of an, which is just the limit as n goes to infinity, and an is that, so n factorial over n to the n. But you know what? This is just nicely equal to 0. Why? I'll tell you by the list. Because n factorial is smaller than n to the n. Yeah. So that's pretty much it. And then just to be proper, we can say an, which is n factorial over n to the n, does converge and converges to 0. So this right here is it. Now, if this is the question, then we are going to test, right? We pretty much have the series as n goes from 1 to infinity, and we are looking at n factorial over n to the n. For this right here, unfortunately, we cannot say it converges to 0. It has no connection. Once we do this, we end up with 0. That's too bad, because we really don't know what will happen right here. But if you look at this question, well, all we have to do is the ratio test, because we have the factorial and also the n in the exponent. So it's a good idea to use the ratio test. So let me just write that down real quick. Ratio test. And to do so, we are going to check we're going to check the limit as n goes to infinity. And let's go ahead and just put down n plus 1, right? an plus 1. So this is going to be n plus 1, and then you factorial that over n plus 1, and then n plus 1. And you do the reciprocal, so you multiply by n to the n over n factorial. Check this limit. Right now, let's see. Open the factorial. This becomes n plus 1. Right, you put on the inside first. And it goes down by 1, which is n. And then you multiply by n minus 1, and so on, so on, so on. But that's just n factorial. This and that cancel off nicely. Now, fix the exponent here. This is n plus 1 to the n times n plus 1 to the first. Have a look. This and that cancel out. So we have this and that left in the absolute value. But the absolute value doesn't matter because everything inside is positive. So this right here is the limit as n goes to infinity. Let's just write this down as n over that. N over n plus 1 raised to the nth power. Well, if you put infinity to here, you get 1 to the infinity's power. No good. But this is really similar to the limit. Sorry, the fact. Just do it real quick. Limit as n goes to infinity. Do the reciprocal. We get n plus 1 over n. And by the way, this is such a classic example for sequence and series. You should know this like by heart. Yeah, a very popular test question, just to let you guys know. Anyway, continue. Split the fraction. This becomes the limit as n goes to infinity. And then 1 plus 1 over n raised to the negative nth power. This right here tells us a is equal to 1, b is equal to negative 1. Thus, this is e to the negative 1 power. And now, what does this do? What does this do? This is 1 over e, good, but what does this do? Can we draw any conclusion? And remember what we are trying to use. Dark, can you mention why it converges? Why? Like, why does this tell us that this right here converges? Yes. Jonathan, you are right. Tony, you are right. Don't just put a limit right here like e to the negative 1. You have to mention that this right here is less than 1. Therefore, we can use the ratio test and say this guy here, right? It does converge, and here we have to give a reason though. It converges by the ratio test. Yeah, so that's that, right? So for the first question, you just do computation. And for the second one, you are doing the series convergence tests. And there are a total of 10 of them. Yeah, so just like that. Okay, good. All right. Okay, of course, if we are talking about power series, how can we not talk about the best friend, right? So for number 12, we will do the power series for the following function. So here we have number 12, and then the function is, I would just say we want power series and also the radius of convergence and also the interval convergence, right? For this guy, we have x to the third power over 9 minus x squared. And again, if you want to see how to come up with power series, I have the power series marathon video for you guys already. 4 hours, non-stop, 26.2 power series, right? So go ahead and check that out. But we just have to do this for question number 12. And this is how we can do it. I'm just going to put down our best friend, of course. Recall that when we have 1 over Recall that when we have 1 over 1 minus x, this right here is equal to the series as n goes from 0 to infinity, and you just have x to the nth power here. And don't forget to mention that the absolute value of x is less than 1. Namely, r is equal to 1. And remember that for the best friend, the interval of convergence goes from -1 to 1, and you do not include the endpoints, right? So this is like the blueprint, literally, because it's in blue. Anyway, let's see what we can do to make this happen. X plus third power over 9 minus x squared. All right. In order for us to use this, we must have a 1 on the top. This is x plus third power. It's okay. Just put that down first, and then let's say multiply by 1. That's legit. Good. Moving on to this, we must have a 1, but this is a 9. It's okay. Just factor out the 9, like so. And then when we do that, factor out 9, we will get the 1 that we want, and the minus match. And don't forget that this is x squared, but we factor out the 9. So this is really x squared over 9, like this. Okay? Okay. Now, let's see what we can do next. This is still that, which is x to the third power over 9. But this thing is the same as that. We just have to plug in this. So this is just going to give us the series as n goes from 0 to infinity. And you put this right here, parentheses, x squared over 9, and then raised to the nth power like that. Now, fix this a little bit. Let me just make it slightly more clear by writing this down one more time. And this is the series as it goes from 0 to infinity. Let me write down the coefficient first. So we will have 1 over 9 to the n, and then times x to the 2n, like that. Now, we can multiply this in with x, and we will also multiply the 9 here. So, oh no, oh my god, this is equal to the series as n goes from 0 to infinity, and we have 1 over 9 to the n plus 1. We just add the exponent. And then, of course, you add the exponents, x to the 2n plus 3. Whew, just like that. Are we done though? No, because we still have to figure out the r and I, which is this right here. Not so bad, because earlier we plugged in x squared over 9 to here. We can do the same right here as well. So we just have to work out the absolute value of x squared over 9, and we set this to be less than 1. Check this out. We can put a 1 over 9 in the front. We can put a square on the outside, like so. This is less than 1. We can multiply both sides by 9. And then we can take the square root on both sides. So, yeah. And with this being said, we can see that r is equal to 3. Therefore, I, because the center is at 0, so just move to the left 3 times and also the right 3 times. And because we just did algebra with the best friend, so the interval of convergence stays the same. Parentheses, parentheses. Whew. Done. Just like that. Why not plus or minus 3? Because we have the absolute value already, so x is always positive. That's why we can legitimately take the square root on both sides. And if you want to see the proof for why the absolute value of x squared is equal to that, I'll show you real quick. Because this means absolute value of x times x inside, right? And now, the property of the absolute value is that the absolute value of product is the product of the absolute value. Thus, we can write this down as absolute value of x to the second power. Yeah. And thanks to absolute value always being positive, you can just take the square roots on both sides. And you don't do the plus or minus. That's much quicker for that. My arm is tired, actually. All right, so last question, right? Number 13, last question. For number 13, if you guys haven't seen the file, then just take a guess. Is there anything that we haven't done yet? We did a test for divergence, ratio test, we talked about the root test, telescoping series, geometric series, power series, best friend, and integrations for power series and things like that. And there's one more test that we should be talking about, but we haven't done yet. And of course, let me just write that down for you guys first, and you guys can tell me. Number 13, we're going to test this out to see if this right here converges or diverges. And if you think about what I said earlier, you can kind of expect that there's the test that we should be using. So which test shall we be using for this? Is this a real beer? No, it's fake. I got it from Amazon, $7.99. $799, not $7.99, okay? Jackie, we used the integral test. That is correct. See? We haven't done the integral test. This is the one. So, let me just indicate this real quick. We should do the integral test. Why? Well, because if you do any kind of comparison, it's not going to work out the way you want it to be. You can try the limit comparison test, no. Direct comparison test, no, right? But for the integral test, the reason is because if you let the function just replace all the n with x, you get 1 over x, square root of ln x. You can integrate that relatively easily, pretty easily I would say. And let's just see. Just go ahead and graph your function on your graphing calculator or so, and you get the graph looks like this, right? Somewhat like that. But anyway though, just go ahead and mention that f is continuous, positive, and decreasing on the interval x is greater than or equal to 3, right? Yeah. So this gives us the right to use the integral test. Therefore, we are going to check the improper integral going from 3 to infinity, and we have 1 over x square root of ln x. Haven't done integral for a while, huh? It's not so bad. Let's see. Let u equal to ln x. That's the key. You see that du is equal to 1 over x dx, and then of course you can isolate the dx, which is what I prefer the students to do. So we get dx being equal to x du. Alright, we will finish everything there. You will though. Have a look. When x is 3, put it here. We have the integral, and we will have u goes from ln 3. And when x is infinity, you put it here. This right here, u will be infinity. And then we see this is 1 over x. And then we have the square root of, this is just the u. And then we have that, which is x du. And yes, if you do this, you can see the cancellation very nicely. And now, as I said, we are going to do everything that you world. Have a look. This right here, we just have to integrate from ln 3 to infinity. Look at this as u to the negative 1 over 2 power du. And then just go ahead and add 1 to the power. And we get positive 1/2. Divided by positive 1/2, we get multiplied by 2 over 1. So this right here, we pretty much have to do 2 square roots of u, and we just have to go from infinity to ln 3, right? Well, sorry, ln 3 to infinity. Technically, I just say it like this. So if you just plug in, then you get 2 square root of infinity, and this is technically taking the limit. But we can draw a conclusion on this real quick, so this notation is not bad. And then plugging ln 3, so you have 2 square root of ln 3. this guy is infinity. This is finite. So all in all, this right here is just infinity. Therefore, this improper integral diverges. Therefore, that infinite series also diverges. I will just write down the conclusion for you guys. Conclusion, right? Conclusion. So let's just go ahead and write that down. The series as n goes from 3 to infinity, and we have 1 over n square root of ln n. Also diverges. Why? Let me spell this out just to be legit by integral test. By the integral test. Whew. Factorial this. All right, so that's it. Finish everything. Okay, so take a look. If you guys have any quick questions, just leave in a chat right now, and then I'll try to answer your questions. Also, Michael, you are talking about the series of n to the a ln b to b ln n to the b's power. Oh yeah. So that's a lot of fun. And usually you might want to do integral test or maybe comparison test depending on the power of n and also that. Yeah. All right. Thank you as well, Alan. I like your answer though, but like because it's live stream, so I wasn't taking your answer. On the exam, I will take your answer. Yeah. If my students can come up with an answer like that, I will be happy for it. Yeah. Right. Let's see. Any questions? Anything you else want to talk about? Jorge, what? Oh, were you talking about the one on the test? Yeah. I think I took your answer too on live stream earlier too. So yeah. I have no idea about that answer. I never thought about the answer. That's why I was so shocked when I saw your answer, like the series of 1. Because it fits all the conditions and also it answers the question. So I cannot say anything for that. You will give 10 out of 10 for that question. All right, so that's it, and then we will be done with power series, and next week I will think about what I would like to do for the live stream, and yeah, thank you guys so much for coming. I will see you guys next week. Bye.